Yeah, so what we've been doing so far, we kind of move on from that to looking at some calculation questions. So before that, I just want to give you some overview of other ways of generating these random graphs. Okay, here is a simple question. Suppose you want to create a population with two types of individuals. Population with these two types of individuals. So you can think of population as bunch of nodes. That's what population data means. Okay. So type 1 will have and one neighbors, and type 2 M2 neighbors. Is there a way to create a graph where you can satisfy this property? Very simple problem.
We can consider two different graphs and take their union.
Okay.
So that one graph has each node has the degree M1 and the other graph has each node degree.
Create. No problem. I can create.
So, there is no constraint on type 1 has to be connected to type 2.
You just have M1 names. Also. It could be that type 1 is only connected to type 1, type 2 is only connected to type 2. Okay. You can take the union of a single graph, a union of two graphs. So individually, they have the right number. How do you do that? Think of some random. Don't think of a deterministic construction. That will be lovely. So you can replace M1 by, let's say, expected degree to be. That will be allowed. See, neighbors is nothing but degree.
Yes.
So far, we have not really handled such a case. What we've done is we assign certain way of generating a random graph. For example, it was Ardo-Shreni graph or differential attachment graph, for which something came out. Now you can choose particular parameters to say, okay, this is F1 or something. But that is a little too much to do. So in particular, in let's say in Ardo-Shreni graph, you could possibly create this type of graph. How would you do that? You will not be able to create a mix. That is clear, but at least one type you should be able to create. What was my parameter then and PL? So if I pick PL equal to M1 divided by N, my expected degree is M1. Right? So whatever graph I'm saying, I have expected degree M1. Similarly, I can create another graph with M2, possibly put them together. But that's an ugly way of doing things. When you generate a single graph, here you can ensure that something like this happens. Think of any static. Okay. Yeah, don't think of what we've done in the class. Just think of as an exercise, what would you do?
So, suppose I want to create N1 nodes of type 1,
Fine.
2 nodes of type 2. I'll take N1 and N2 nodes. And from each of these nodes, I'll create stubs, and then I'll randomly connect the stubs so that everything is connected.
How many steps?
So each node, N1 will each node of
So
N1.
let's use color here. So blue is for type 1. Red is for type 2. You just tell me for one of them.
So the blue one will have N1 stub coming out. And the red one will have N2 stubs coming out. And
Now what should I do?
then I'll randomly
So pick a pair randomly.
and connect.
Okay, what will happen? Why should it have a degree? It won't. Why is it compatible?
If I'm able to get a
Because some of them might not even get anything. So in this, because M1 is not necessarily equal to M2. Does everybody find the partner?
if everybody finds a partner, then I'll get a partner.
Okay, but what's the guarantee that you get a partner? For example, just take one blue node and one red node. Whichever one is smaller, I will only get that much. The rest of them, what should I do? Groups. Simply groups.
If I have lots of nodes, then it might work out.
Yeah. With some high probability, something. So think of putting this this way. Somehow find a generative model where the probability with which build the connection between the pair I and J is given by some function. Think of it that way. So don't think of doing things for one node at a time. Think of it for a pair of pick node Vi, pick a node Vj. Think of a model with which I can put certain probability with which an edge exists. For the understanding that it was very trivial. It was just little p. Little p, it didn't really matter which pair I chose. And can you make it pair dependent as well? So I'm picking Vi and Vj, the probability with which there exists an edge is a function of I comma. Can you put any function on this? That some reasonable choice of Pi. There's no one right way of doing it. I wanted to create it. In this case, suppose I wanted 1 degree out for blue and 2 degree out for red. What's a reasonable function for Pij? So I'm not going to create these stuffs. All I'm going to say is this is a blue type node, this is the red type node. An edge exists between them as a function of right. So now what is a good function? That's much more direct. So let's suppose I assign a weight to node Vi and a weight to J to Vj. How can you think of Pij, the function of Wij, Wi and Wj?
There can be many functions, but how to correlate with M1 and M2.
That's only one example. Pick a reasonable choice and defend that choice. As I said, there is nothing right and wrong about it. For every function you will come up with, you'll give rise to a different graph.
for this, we can take the Pij to be
Mhm.
1 by I plus G.
1 by I plus J. What does that mean?
Since I is the ith node.
The index of the node should not matter. Right? What I'm assigning is the weight to each node.
So we can take the reciprocal of the sum of the weights.
Okay.
1 by Wi plus two.
So P by J will be equal to this
1 by Wi plus two.
this one.
No, 1 by completely open. Wi plus two.
But does it satisfy the basic property of the probability? At least that much should be very much.
Weights are
Non-negative. Weights
not
are non-negative. That much is given. Because you're doing it for yourself. But you're putting Bij equal to 1 by this. Now, probability should somehow satisfy some property.
okay.
So one interesting derivative model which is very well studied in Bij is equal to Wi times Wj divided by the defined model is plus divided where L is nothing but the summation of all the weights. N nodes. But think about what does it even mean? Definition is clear. Just taking product and normalizing it. That's all I said. So we definitely give rise to a random number. All I've done is I've associated weights to each of the vertices. And once you have defined that, I'm just randomly putting edges between them depending on the divided edges. But it's not completely local either. There is a Ln, which is a global phenomenon. It's not a completely local rule, unlike the Hadosini. But can you recover the Hadosini example?
When Pij will be same irrespective of I and G.
Yeah, but when I say recover, you have to give me a certain choice of WI. What is that certain choice?
Each are assigned weight 1.
It won't work. See,
1 by
1 by 1 plus
N
n.
plus 1.
That's not the Hadosini.
Each Pij will be 1 by N plus 1.
Yeah. So, but that's only one particular test.
Yes.
Suppose I wanted Pij equal to lambda by n. Do it. Whatever that lambda by n. So I want you to carefully look at what have I done. So, is it general enough what I'm trying to do?
If you replace WI by the expected degree of errors, then
Expected degree of what is very much. It's just n times PM. Will it work? With n times 12, there will be n square here. Something will seriously go. While denominator will also n square. It won't cancel out next. You have to slightly juggle something to get back your result and write down. But what I wanted to notice is that this seems to be a general way of doing things. So can you identify one simple property in this, that when is Pij large? When the weights, both weights are large. What if one is large and other is small?
It will be small. Pij will be.
Not necessarily. What am I trying to compare? I'm going to compare against small and small. So the three ranges I'm able to create. One is large and large, large and small, and then small and small. So what kind of graph will be resulting if I choose my WIs carefully? Can I go for the full spectrum? One is a very homogeneous graph like a Ardosani graph. Vertices are indistinguishable. That's one way. This is the other one extreme. Can I go all the way to the heterogeneous case? Where there are Amitabh Bachchans, there are Brad Pitts in the world, and rest of us have no followers. Can I go to that extreme? To give you an example where I can do that, as heterogeneous as I like.
When there will be huge difference between Wi and Wg, Eij can be very small. Like
No, so I can control that. That's the point. It's in my hand what WI and WG are. Which I can control that. But can I generate a graph I want to generate? That's the question.
in this model, so two nodes with very high degree are very much likely to get connected.
No, we're putting a weight. Everything else is going to come out from there. So weights, the three regions, right? High and high.
Weight is not proportional to the degree.
No, weights is it's the other way around. Degree is proportional. So first you assign a weight, then you find the probability with which a edge exists between a pair. That is determined by WI and WG. So if a particular vertex has a large weight, it's also expected to have very large degree. Because for many J's, the coin toss will turn out to be 1. Question is, what should I do if I want to generate a heterogeneous graph? Like a social media graph. What would be my choice?
In a heterogeneous W.
Yeah, but what give me one choice? Because as I said, if WJ is small, WI is very large, the multiplication can end up being small.
So we can draw W from a heavy tail distribution and that.
Okay, but that could also very small values also. So 1 seems to be a problem. That if anything goes below 1, might get scared. So the simplest fix could be that all W is greater than 1. Okay, and then you can appropriately choose WI is large enough so that no multiplication will ever be. So as long as any distribution you take, but which is lower bounded, or the values are lower bounded by 1, you should be able to create a graph which you want.
We can filter out.
Then you can also do that if anybody is small. But this will be a very simple generative model. That if a WI is large, it is expected to have, I don't have to artificially go and manufacture something for it. So all I have to do is just to assign a large weight to a node which I expect to have plastic. So in particular, I should be able to recover the preferential attachment graph. If I want.
I didn't get why I mean greater than 1 thing.
Okay. If it's not greater than 1, your argument was that I can multiply it with very small number. I get a very small number.
Yes.
But what can I stop? By making sure that WJ is never less than 1. Then if a large number multiplies a number greater than 1, it never becomes small.
So what was the issue of having an weight to be less than 1?
You tell me. you argue that if one is large, other is very small, the product will be small.
Yes.
How do I stop it? By making sure that the weights are at least one.
Okay. Yes.
So it's a simple fix. Otherwise, I can do it, but I just wanted to make sure that you are happy. So I can create whatever regime I want. Very large, large versus large, large versus small, and small versus small. So most people are small versus small. So they'll have very few degrees. Large will have a very large degree. And I should be able to create it within a. Now, so an exercise if you want to do that can recover. PR n comma lambda by n by choosing yes. How much? End up getting exactly PIJ equal to. Put it back to the sorry. Not a very complicated exercise. You get your. This is just to show that it's a rich class of graphs. Because we already covered, we should be able to do more stuff. In particular, a graph of this type. Okay, so now suppose my exercise is to create this graph. Just type one nodes of degree M1 and type two nodes of degree M2. Then I generate this using this class of graphs. All you have to do is to assign weights. There is nothing there.
We would have done two different weights.
Yeah, you can possibly choose two different weights. What do you want to do for what? This is an obvious choice.
We would assign two weights and restrict the expectation value.
No, but tell me what weights are. But that is not, you'll assign a particular weight, that is not a particular weight. What is that? How much?
M1 by M1 plus M2.
Okay, that's super complicated.
And for the others, M2 by.
But think why are you normalizing?
Why are we normalizing it?
Why are you normalizing the weight?
So that the summation of. No.
There will be reason to normalize. We chose W like two types of weights, weight of all type of individuals to be M1, all type of individuals to be M2. As simple as that. What happens? Does it satisfy my requirement? What I will do is to compute the probabilities of two types. P11 and P12. As you can do similarly for us. P11 is between type 1, type 2 individual, and P12 is between type 1 and type 2. So rather than computing, try to like give an intuitive argument why this should work or why it doesn't work. What is P11? P11 is simply M1 square by summation of, let's say, M1 M1 plus M2 M2. M1 is the number of nodes of type 1, and M2 is the number of nodes of type 2. Okay. And similarly, P12 is M1 times M2 divided by Ln plus M1 M2. What is the expected degree of a type 1 vertex? Oh, I want to create this type. Yeah. Type 2 graph. Degree M1 and degree. Let M1 be the number of type. Oops. So N2 type 2. So by my definition, Ln is, so I'm defining Wi equal to M1, where I belongs to type 1. And similarly, J equal to M2, J belongs to type 2. So what is my Ln? It's simply M1 times M1 plus N2 times M2. What is the expected degree of a? Expected D of 1 means of type 1 node. How many is it? There are M1 minus 1 other ones. And what is the probability with which I connect? M1 square by M1 into M1 over N1 and M1 plus N2 M2 plus M1 times plus N2 times M1 M2 over N1. Who was so good? Oh, how much is this summation? What does it roughly look like order wise? So suppose we have simple observation that M1 square plus M1 M2 is little O of Ln. It's order wise smaller than this quantity or this quantity. Can you say something about what the sum looks like?
How you got this expectation value?
So what am I doing? Putting a weight for each type 1 vertex, VM1, and each weight type 2 vertex to VM2. What is Pij? Pij is exactly this. So P11, an edge exists between a vertex of type 1 with another vertex of type 1 is this probability. And then how many of them? N1 minus 1. Similarly, probability, so this is P11. All of this is P11. This is P12. Then how many such type 2 nodes? Into. So suppose this is true. What does it really mean? That weights are not too large compared to this. Where so n's are large. That's essentially what is going on. In that case, what can you say? essentially by visual low plan, I can just take this guy off, take this guy off.
Yes.
What is the meaning? M1, it comes out common. L1 minus 1 times M1 plus N2 times M2 divided by Ln itself. How much is this? Under this condition, this is equal to M1 times M1 N1 minus 1 over Ln plus M2 times N2 over Ln. But what is M1 N1 plus N2 M2? Ln itself. So essentially, this is close to 1.
Okay.
What I end up getting is M1 itself. So the difference is just 1. It's 1 by Ln. That's pretty small. So I can essentially expect the expected degree to be very close to M1. If I'm doing this, as long as N1 and N2 are large enough. So if the population size is large enough, assigning each of them M1 and M2, I'm going to get this obvious. So the expected degree is going to look like. Similarly, you can do for expected degree. So this model is in fact a very rich model. The examples we are seeing are very specific, but you can just keep expanding this horizon and get whatever graph you have. Okay. Any other observations you want to make for this model? What other graphs would you like to consider? Raj, any thoughts?
Could have more than 2 types of vertices. M1, M2, M3 neighbors.
This is really very.
Hello,
Can you speak again?
can you hear me?
Can you say again?
Hello. Yeah.
Yeah, now we can hear you.
You can have 3 types of vertices.
Okay, and what will happen there?
Type 1 would have M1 neighbors, type 2 M2 neighbors, type 3 M3 neighbors.
And what should I choose my weights to be?
Yeah, I was thinking into W.
The obvious choice would be just simply take WI equal to MI. But does it work out in the case of population of 3 different types? Let's see, not see this. So here, what would I get? I get M1 times M1. I get 3 types here. So that's yeah. So as long as I keep the condition true, I get M1 into this essentially plus M2 into N2 plus N3 into N3. There's no other reason suspect something should go wrong. Anything should go wrong. Appears to be a sound strategy. Okay, but then if you can do it for 3, you can do it for any number of types. Is there an interesting implication in this? So there has to be some place where you have to stop doing this. Because of the condition that M1 square plus M1 M2 is little O of ln. So you can't go all the way to creating n different types. So suppose the total population size is n, you can't go to the having n different types of graphs with n different types of things. So it has to stop below a certain level. So it has to be little O of n. The number of different types you can possibly create has to be little O of the total number of nodes in the graph. Yeah, but I think you should be able to anything between that we should be able to start. What about power law distribution? Can I create a choose weight such that my degree distribution looks like a power law? No. Categorical no. See, those are the interesting degree distributions we have seen so far. One was adversely negative homogeneous, but with attachment gave rise to power law. We also expect to see power law in real world networks. So now, if I want to use this derivative model, then I somehow create a graph which looks like a power law distribution.
Power law means heavy tailed.
Just always remember x to the minus alpha. So the probability that degree is equal to k is proportional to k to the minus alpha. Alpha is greater than 1.
No, right? Because of the heavy tail, this might become larger than log n.
What might?
So denominator.
I don't, this is one way of creating it. I'm not saying you pick W1 equal to R1 and W2 equal to R1. I'm not saying that this particular way of making it, but the graph has been defined where Wi can take arbitrary weights. I don't have to necessarily take only 2 possible. I'm not saying you take only 2 possible weights and tell me how to generate a power. Saying you're allowed to put any W1 to W1, then you create a power law distribution.
Again, in that case, you'll have to calculate the expected degree and is it enough to draw W from a power law distribution?
Can you guess what kind of distribution?
What kind of?
Distribution, if W I take, it doesn't even need to be distribution, it can be some deterministic quantity, which might look like power law. See, W is completely arbitrary, you can choose whatever. So what is a good guess for WI? Suppose WI, but could actually be able to guess it. Can you show it or not? That's a more complicated stuff. But what do you expect WI should look like? See, WI also controls the degree. Right? So if you want a power law type of behavior, what do you expect? Some nodes to be very high degree, but quickly degenerating into smaller degree nodes. So if I were to ask you what type of WI should look like, not to prove directly, but think of it. What do you expect the function WI to be? Does something like this appear to you? What type of function is this? What do you expect to happen for such? If I make this choice, what do you expect the graph to look like?
As I will increase, this will increase, but the value will lie less than 1.
It is okay. All we care about is relative weights. We don't care about absolute weights. The way I'm indexing is I going from 1 through n. Just that for convenience. W1, W2, what do you expect W1 to be better than W2 in terms of degree, or W2 to be better than W1? W1 is increasing. It keep going towards 1.
Yes.
Starting at the smallest and it keeps going. What do you expect? So most nodes should have a vertex edge between them. So what type of graph we expect to see? Resulting from this choice of weights.
We have very less,
Sorry,
very less.
that's not. We're not interested in overall what is the number of degrees. Okay, so let's slightly formal and then compare to see what I said. Oh, so for the moment we're interested in WIs with deterministic, but you can do all of this with respect to WI being IIDSF or correlated if you want. So they themselves can have a distribution. So the quantity I'm going to write will be a random quantity if WI is a random. What I'm writing FNX. Like this notation, but I'm going to stick with the book. Here is 1 by n. WI is the next. X greater than 0. So what am I counting with f and x?
The fraction of vertices having.
Weight less than x. So it's like empirical distribution function. I would have liked to say probability of wi being less than x, but there is no such probability right now. So they're not assigned anything. So that's why I'm just writing it as empirical. Distribution. So if wi is a random, this is the random quantity. Notation. Use a random index. U. We will define Wn with the weight of this random vertex. So, observation. What is the connection between Wn and Fn? What is the relationship between capital Wn and Fn? Is there any relationship between them? Is the relation between if I'm just picking one vertex uniformly randomly, whatever its weight is, I'm defining it to be Wn. What has Wn got to do with Fn? What would be distribution of Wn? Where the randomness is over the random choice.
Yes.
What would be that?
The definition of Wn is the distribution. Same as that.
Is exactly a distribution. These objects by now should be just natural, it should come naturally to you. Distribution. What am I doing? Just going around the whole graph, picking one uniformly random and defining that weight to be this. This is just written in the different form. That's it. Because this 1 by n is nothing but the probability with which I'm choosing each vertex. What is the once I choose whoever, that's exactly what I'm going to see. So it's a redefinition. Oh. So certain conditions are needed for proceeding further. It's called the regularity conditions. There exists F, which is a distribution function. You understand what a distribution, usual properties of a distribution. Remember, the generic is x x. Satisfies certain properties. It goes to 1 as little x goes to infinity, is always non-zero.
Increasing.
RCLR, right continuous left limits. So that's all I'm asking, that there exists an F, which is the distribution function. That means it satisfies all this. Yeah. These are not being proven, these are being asked. that there exists an f, some for which as n goes to infinity, Wn in distribution converges to W, where W has distribution function. Technically, what we asked is that when it converges to F in distribution, that there exists an F for which this happens. It's just a roundabout way of writing it. And this is A. And so these are not necessary, it just makes people's life easy. So for further analysis, which we are not going to do in the class, I just state certain results. But I wanted to point out that these are necessary. And the limit expected value of Wn then goes to W has distribution function, the same thing. So these two regularity conditions are needed for analyzing this graph model, the graph generation. We do certain more things, but we'll skip those. Okay, so now we can talk about. So now we should be able to think about if I specify an f instead of right. See how is f coming? F is a limit of fn, literally. If I want a particular f, that's what this means. This is my particular choice of wi's, which is giving rise to fn. This is fixed given wi. And fn converges to f that exists somewhere. So if I start reversing the process, and I want a particular f to which fn should converge, I can always demand that. How should I select wi? So in the differential attachment model, I have a particular f in mind. Okay. So I should be able to reverse this process. Is this clear what is going on? I'm asking here if there exists an f for which fn x converges to f as n goes to. So for large enough graph, fn will be very close to f. Now if I have f in mind, can I generate a graph which is large enough? Which is close enough to f. So that will give rise to some way of creating these wi's, which correspond to this f or close to this. So, what is the f when I'm looking at the heavy tail distributions? I have a particular f. Can you now guess what wi should be? F of x is very easy for a heavy tail distribution. Just 1 minus 1 by x to the power. So given that, can you come up with a strategy where I can identify wi? Is the strategy clear? Otherwise, it's a difficult one. Strategy should be clear what I'm trying to do. So I'm trying to aim to get my wi in such a way that fn converges to a particular f, where f is given to me. So now is there a generic way of creating wi's such that all of it makes sense? So if I give you f, you should be able to write wi in terms of fn. Another way to put it is that in the formula above, if I substitute for wi as a function of f alone, can you show me that fn the left hand side is very close to f itself? So look at the right hand side. It's only a function of wi. What is my aim? That fn should be close to f. So if I write wi only as a function of f, right hand side would be a function of f, left hand side would be a function of f and x. So what is the reasonable choice of wi? Such that f and x on the left hand side and the right hand side is only a function of f, they're close to each other, they're not too far away. Because I want f to converge to f, I don't necessarily have to have equality.
wi equals to f.
wi equal to f, what do you mean? It has to be a function of I, right? You're not thinking correctly, that's why you're giving this answer.
wi is such f of x is less than equals to y equals to.
Okay, so suppose we are given that. Does this appeal to you? So we have 1 minus inverse of u into x. That's 1 minus x. So it's slightly more generalization than we have seen f inverse. If you remember. If it's a forward function, I can always take the inverse map. So this is 1 minus f inverse. That's all. So this is the definition. Now this is my definition. What is fn of x is the question. That's all I have to know. This is my definition. How I came up with it, we'll see why it makes sense. Eventually, like everything in the reverse direction. You remember the definition of f inverse? F of x, everybody understand? F of x is the x less than equal. I can always move the inverse path. That is of f inverse x. This is something more. This is 1 minus f inverse. Let's see why that 1. So f inverse u is very similar. In for x f of x. That's your definition of f inverse. This is 1 minus f, so that is why this inequality is there. Okay, now all I have to do is to compute f and x. And if this is somehow close to f, I'm done. Right? That's what I really want. The Fnx should converge to F. It won't be equality, but as long as I can show that this is close enough to F and then goes to infinity, is getting there. I'm kind of done. So now it's a concrete construction. So let's try to do it. So what is Fn of X? In summation indicator Wy is an equal to X. Right? So when I switch or apply Wy, what will happen? So just one more write in terms of F of X. Instead of I, inverse. Is this okay? Whatever that. So this is I going from 1 to n. I'm writing j equal to 0 to n minus 1. Subtracted 1 index. So just put a 1 minus j. So I by n. What have I done? Essentially subtracted 1. Nothing really interesting. By putting j equal to n minus 1. That's all I've substituted. This redefining the summation. And interestingly enough, what is this equal to in terms of 1 minus f inverse? We have this equation. Can you write something of this form equal to this? Nothing to do with that. Just brute force definition. What is 1 minus f inverse of u? Infimum of x, 1 minus f, x to be less than equal. What is this f inverse of u? Infimum of x, fx greater than u. Even if you can guess, it's okay. This is the bad 1 minus f. By definition, this is
1 minus u.
yeah. I'm going to use this here. Now you see it is 1 minus f inverse 1 minus u. Where u is nothing but j by n. It is equal to the f inverse of u. Substitute that. right? Now, what can you write this in terms of f(1)? You can move it and also about it. It's indicator j less than f of. Look at my starting point. What was my definition of fn of x? So using that, I can get it equal to y times n of x. There's some feelings and flow. Worry about them. This min never more than one. We got here. So now what is the definition of fx? It is 1 by n, so I can always move it here. So 1 by n summation over all indices. So I have to correct for that. But other than that, you look back at the definition. Fn of x is 1 by n summation I will w to be less than x. So whatever I got here. J less than equal to n times f of x. Can I go from here to here? You can. So look at the big picture. What have I got finally? Fn of x is 1 by n times n of x plus 1. That's really what I got. So how will this look like as n goes to infinity? Essentially look as f of x. So this is a reverse procedure as long as those regularity conditions are satisfied. And this is an exercise in the book where it shows that for this particular choice, this holds. Then you can actually do this. So this is one way of actually doing backward fitting. So you want a particular f, you generate wi according to this. So as long as those regularity conditions are there, here. So now you know f. What is the particular f for the power law distribution? F is simply f of x. X to the power minus tau. Well, not x. So 1 by x to the power. This you can get your w to be exactly that function arrow. This function is what you invert that. So give you a constructive way of finding where a large graph should, if you want it to converge, how should you select your weights? But there is a catch. One has to be careful about the regularity conditions. The regularity conditions better be satisfied. The reference should better converge to it. Okay, so what's the takeaway so far? I want to make sure that whatever we do stays with us. I don't want to overdo things.
Even we can design our weights to get the design.
But it's kind of interesting.
That's very practical.
Yeah. That's how the generative model. See, that's why it was important to generate in this particular way. If you suppose you remove this ln, possibly not be able to get it. See, another way to do this is wi times wj, sum over all possible pairs wi wj. That's an equivalently reasonable model. Somehow that is not as analytically intractable as this model is. So this asymmetry being ln is just simply the summation of weights. It's not summation of the product of the weights. ln is simply just the addition of weights. One would have expected it to be summation of the product of symmetry. So it's not symmetric. But the beauty of this is that you can actually do complicated stuff using the regularity condition. That if you have this condition, then you can go backwards. That you are given an f, here is a way to generate weights so that the degree distribution will appropriately as n goes large. It's a very nice way of constructing random variables. So I don't know. Have you ever seen? So if I wanted to construct a random variable, I only give you a uniform random variable. You know how to do this? So I give you access to uniform random variable.
Yeah.
But I ask you that the random variable I want has a particular distribution at X. You know how to do this?
Initially, do this on the transformation method. And
Exactly. So this is precisely something like this. I've given you a particular f, you're generating W certain way, the resulting fn is very close to f. Alright. So now I'll just take a couple of results which are interesting.
In the fourth slide, 1 minus f equals 3. 1 minus f is itself a function.
That's right. Otherwise, I could not define an inverse of. You should really think of tracking from here. This is you've seen before.
Yes.
From here, you should go here. And then go back to saying that is. This is slightly artificial without looking at this. And that one is to adjust for things like so. That one is essentially setting unnecessary. But you should really think of this f inverse of u. If you remember, we did very early on that if u is uniformly distributed, you apply f inverse on that. Resulting function has the distribution function there. Something like that is at play. You should play around with those things. That if u is uniformly distributed, you apply f inverse to that. The resulting random variable has distribution which is S. Oh. So the result is in fact slightly stronger. That 1 by n times the number of edges in this graph generated appropriately over W-wise. Converted probability to 1 by 2 times the W. Where W has distribution F. Remember, W is defined with respect to F. W in distribution goes to W, which has a distribution. Slightly easier one to show is that the expected number of edges. This is not expectation. It's just the number of edges. This is equal to this by n. Then 1 by 2 times. Let's try to look at this quantity. Can you estimate this quantity? Forget about the right hand side. The interesting quantity. The expected number of edges in this graph. What did you say? Remember, it's just the expected number. So what is this equal to? Summation Pij really. Correct? I don't want the belonging to 12. These are the expected number. And how much is Pij? Equal to WIW over LM. What's WIW? I want you to upper bound this quantity. In terms of LN alone, can you do it? In terms of LN alone. What can we drop from here? We can upper bound. Oh, let's do that. This is simply over ln. We just move the summation. How long is the summation compared to ln? So I didn't realize it at the first time I looked at it. This can be bounded or rather is equal to some function of ln. This is equal to ln. This is equal to ln square. Yeah, it's not obvious to look at it. First time you look at it, it's not obvious. This is a double summation, right? So let's suppose you freeze one particular index. You're adding everybody else. And that is exactly it. So it is W1 times ln plus W2 times ln. So ln comes out. This is the same. And in this, the half is added to make sure that you don't overcome. Because both ways you're counting. So that's just to make sure that. So this is in fact most half times. You can also show that it's not too far away. You converges there. Going from here to here is slightly more. That's essentially. So what you have to show is that this quantity is approaching ln. That's all you have to show it. Any idea why? Do whatever we have done so far. What is ln by n? Yeah. In terms of this. Related to this quantity. What was expected value of W1? W1 1 by n, summing of all the weights. That is precisely where that is. Because of this, that is true. So that ln by n in fact, because of the regularity. So what was the question? Question was why is for ln by n? Why is this? All I showed you this is ln. Take divide by n, and then it should be converted to S2. This is because of the regularity. Because expected value of W1 is converging here. Expected value of W is numbers. So that's how we show that. What all it shows is that you actually say something interesting about the number of edges of this stuff. There are actually more interesting results, and we have no time. I don't want to spend too much time on this. So I want to move ahead next class. And just state one more interesting result. What happens to the degree itself? Let di be the of vertex I. Then this graph. Yeah, so the result is right from the result. There exists something we may have called at degree and Then I just y like that. Probability that vi have not equal to vi. Just try to pass on. What it is saying is that for Zi to be a random variable Poisson distributed, it's highly likely that the degree you're going to see is actually very close to that. That's all it's saying. It's controlling the probability that di is not equal to Zi, where Zi is a Poisson distributed random variable with parameter w.
How is D related to any of this?
G is a new, completely different random variable.
No, G the graph.
G is the graph. We have constructed using this weights W. Let's call it W n comma W. Ith node has a degree di, right? So I'm just connecting that degree with a Poisson distributed random variable with parameter wi. So what is it telling you something very interesting? They're not too far apart. What really happened in this graph was this node I had a weight wi. For node with weight wj, it connected with respect to pij. Okay. All this is saying is that I don't really care what these wj's are. This Poisson random variable with distribution parameter, with parameter wi is what this really looks like. The degree of this vertex I is not really being affected by so many different neighbors. So somehow the correlation is getting washed out. It's a very important result. It's not an obvious result at all. In general, I would expect the degree of I to depend on every other weight of every other node in the network. Right? Because the Pij clearly depends on Wi and Wj. What I'm saying is that if n is large enough, the dependence on every other weight in the network is washing away. That's all.
So if I suppose I chose PIJ, that I wanted a power law.
Yeah.
So
Doesn't matter. Whatever Wi is, this is independent of how you chose Wi.
If graph is large enough, then the degree of each vertex will look like a Poisson.
That's all I'm saying. The possibility that it's not equal to Poisson is small enough. It all depends on what Wi is, what Ln is, and these second moments. It's also telling you the next part that in some sense these are becoming independent. That's what the implication of this really is. Otherwise, Pij should depend on both Wi and Wj. So the degree should depend on everybody else in the network. But it's not. So there should be a corresponding sister result to this. That as n goes to infinity, these guys are actually behaving like independent. So there's some technical condition on right. The degrees di's. So part B, this is A. So if then n will to infinity, max, then B1 equal we are found results and you are welcome to look at it. It's part of the book. It's chapter number 6. You do look at it if you are really interested in this how to construct a particular distributed graph, starting from a particular distribution. You looked at the recipe, that much is there. Now, on top, what more results you want is of this type. And once I do this, create this graph, what does the DV look like? Where is it concentrated? This is telling something very strong, that this is behaving like a person. But for each one at a time. The probability that the DI hat is not equal to that. It's not telling you jointly. That would be even stronger. Where is D1 hat compared to G1 hat, D2 hat compared to Z2 hat simultaneously. That would give it even more strong. There are results of that type as well, but not exactly as much as this. Okay. So that's where I'm going to stop in this word.
If my WI is, suppose I make a random regular graph, then this should not hold it.
No, so if this model is violated, if you're not creating a graph according to this, none of this is true.
So all the WIs are same.
Okay, fine. So what will go wrong? Thing goes wrong. All you have to check is how far is this. This better be bounded. If it's not bounded, then it loses. To make sure that this is
My DI would be some fixed number. And
what would be this number?
if I construct a
WI equal to 1 for all.
for all,
Okay.
for all, then DI would be a fixed number, and this GI would.
So something will go wrong here.
Okay,
Let's check it. But this result is independent of how it is. Whatever for fixed WI, the model next to. No, but your model is not this. Why is it that an edge exists between the vertices equal to 1 over n plus 1? That's not it. That's actually looks like more like Ardo-Schelling. When you take all the weights to be 1 or equal, that's what your edge probability is.
I want to construct a random regular graph each.
Agreed, but what is the choice of the You have to give me that. Is it compatible? First, you will check that your random regular graph can be constructed by putting a particular value of W. If you put all WIs to be equal, you get a graph probability is 1 over n plus 1. That's not what, that's a more understanding.